overslept. And I forgot to charge the car overnight. All right, let's see what the battery level is. All right, it looks to me like 50%. That should be enough to get to work. All right. Another day, another dollar. Get ready for work. Guys, rallying is coming. I love my electric car, but dang, that ran out of battery so quick. If only there was a way to charge your car while moving. Perhaps with an electric road? Dynamic charging?
Okay, so our proposal is about electric roads. My name's Caroline Bowman.
My name is Zarina Catalonia.
I'm Jonah Faustino.
And I'm Rallying Herzog.
So here's just a quick little table of contents. First, we're going to talk about our client, introduce him, talk about background about eRoads, what they really are, and why this is important. Then we're going to go into the scope of work, which includes technical aspects, alternatives, advantages, disadvantages, and our budget and schedule. And then we'll go into the actual research of our proposal, which we broke into these 4 categories, and then we'll finish with closing remarks. So first, our client is Tox Omashakin. He was appointed as the 33rd Director of the California Department of Transportation, also known as Caltrans. Omashakin has a very optimistic view for the future of the transportation sector, as his vision for California features a safe, sustainable, and multimodal transportation system. He encourages the transformative innovation in hopes of achieving his goal of reducing greenhouse gases by 40% by the year of 2030. So all of these reasons are why we chose Tox Omashakin as our client.
So who are we? We are students from San Jose State University studying engineering, and specifically we researched in electric roads. So what are electric roads? Electric roads are pretty much the next step for a future in a green future. So what we want out of green electric roads is to power vehicles, specifically electric vehicles, to sustain and last longer. Why we want these electric roads is because in the long run, it would be cheaper, more efficient, and it would be cleaner for our environment and community.
So in implementing these electric roads, there are a few things to consider. One of them being the technical aspects, like who's exactly going to be working on them. So the engineers and the scientists are going to be responsible for developing the technology of the electric roads. Then you have the construction workers implementing it, putting it all together. And then we have government officials creating legislation that will push for funding for such projects. An alternative we found to electric roads are supercharger stations. So both of these are used as ways to make charging times of electric vehicles, which are traditionally very slow, a little bit faster and more convenient. A couple advantages of electric roads that we'll expand on more later are the fact that with electric roads, electric vehicles can have smaller batteries because they can end up charging while on the road, getting from point A to point B. And with smaller batteries, that's actually better for the environment because they use less resources, like harvesting the heavy metals that end up requiring lots of energy and producing lots of carbon emissions. And then An important one to look at as well is the disadvantages. So the main one being price.
So later stated in our cost and funding section of our work, the budget of this project will be around the $1 billion range. Specifically, it will take about $2.2 billion for installation of our dynamic charging system / eRoads across major areas in the country. Most of the budget will be focused on the three aspects, which are materials, production, and labor. And as you can see in our diagram, we have $1.1 billion allotted to installation, $650 million for materials and production, and $450 million to labor and equipment. Based on this data, it's clear to see that this project necessitates a large amount of money. It is definitely a risk, but if we can complete this successfully, it will be worth it. By doing so, we can eliminate the damage to the environment, which could cause us to spend more to fix later down the line. It will also remove a lot of the need for fossil fuels, as most cars by then will be powered by electricity.
So looking at this schedule, you can see that it's going to take about 10 years to get 10 finished roads. The schedule will be talked about later in the presentation, but for now, this schedule is based on one of the optimal manufacturing processes that we have.
So here's where we break down our proposal into these 4 research sections. The first, which I'm going to be talking about, are the environmental components. So basically, I took a look at how beneficial eRoads really are going to be for the environment. And the first aspect I looked at were electric vehicles, also known as EVs, since these are really the basis for why we're actually implementing eRoads. The benefits of these cars are obviously that they reduce greenhouse gases and they actually produce zero emission while driving. This is important because 27% of greenhouse gases come from the transportation sector alone. So this really just stresses the importance of actually converting to EVs. Right now, the only downside to them is their short battery life. And this is really the problem that eRoads aim to solve. In a recent life cycle assessment of electric vehicles' environmental impacts, authors Dobra, Martis, and Tintelican emphasize that we need completely new ideas and technologies if we want to turn EVs into an attractive perspective. So the next thing I'm going to talk about is peak charging. So EVs are obviously a lot more sustainable than combustion engines when we look at their carbon emissions. This can come from like production, battery, consistent charging in terms of the EVs, gas pollutions. Unfortunately, no electric vehicle really exists without emitting some sort of greenhouse gas at the moment. The majority of charging currently takes place during high demand hours. So this is when people are coming home from work and plugging their cars in. This is usually when solar energy really is not a possibility anymore since it's getting into the nighttime. So now we're pulling from non-renewable sources to charge these cars. And then if you take a look at this graph here, this is a duck curve. You can see current trends for 2020 and then future trends for 2025 and 2030. And although you can see that energy consumption is way down in 2030 during the daytime when solar energy is prevalent, unfortunately, there's a much steeper spike in the duck curve towards the evening hours when we have to pull from non-renewable energy. And this is, again, where the majority of the electric vehicle charging is coming from. In a study done by Roberto Alvarez Fernandez, he says that the key lies in the use of renewable energies to recharge the batteries, leading to a significant improvement in greenhouse gas emissions balance, whereas the use of other electricity sources leads to no substantial improvement or even higher carbon emissions. So here's really where eRoads come into place. In terms of environmental impacts and benefits, as I mentioned before, the transportation sector is one of the most polluting sectors, about 60% of carbon pollution, and the use of EVs would reduce a considerable part of that over time. The goal of electric roads is that now these EVs can charge while they're traveling instead of having to be charged in during high demand hours at home. So now with this system of charging, battery life is greater and we can use smaller batteries. And so this has a lot of environmental benefits in itself, as now we don't have to put as much material and resulting carbon emissions into actually making these large batteries. And this in turn will increase the popularity of electric vehicles, as the short battery life is no longer a restriction, and will ultimately start to phase out standard combustion engines. So next I looked at Siemens eHighway. Siemens is a company and they built their first eHighway in Sweden. And they actually have very little left to do before the actual implementation. Siemens states that nothing is responsible for more smog causing emissions in Southern California than the trucks that haul freight between the region's cities and ports. So they're really focusing their energy towards reducing the carbon emissions of big semi-freight trucks like this one. So they're developing technologies, which we will go into later, that will reduce the carbon emissions of large trucks. So this is important because they're no longer really focusing eRoads solely on electric vehicles. Now it's expanded to electric vehicles and large freight trucks like this one. And then finally, I looked at the implementation impacts themselves. I think it's important to look at not only what the eRoads will do after they're implemented, but also to take a look at what's going on before. So once the technology is in use, it's obviously super beneficial for the environment. However, there are a couple concerns involved with the actual implementation. A recent life cycle assessment studied the environmental impacts associated with 3 different eRoad technologies, which you can see: the pantograph, the IPT, and the rail system. And they compared it to a traditional asphalt road. So this is, as you can see, this graph shows the start to finish life cycle of these 4 road systems and their impact on carbon dioxide emissions. And so you can see that they're honestly not that far off from the traditional asphalt road in terms of carbon emissions, with ultimately the rail system being the most environmentally friendly. But although the constructions of the roads themselves will take a bit of a toll in terms of the environmental impacts, they're really not that far off from standard roads, and the benefits they will provide long-term for the future of electric transportation will far outweigh the implementation factors.
So I'll be addressing the design and methods of the electric roads. So the whole purpose of applying these roads is to reduce 50% greenhouse gases. Today, as Caroline mentioned, that 50% of carbon is emitted by transportation. 23% is from strictly these semi-trucks, as Caroline mentioned before, with the company Siemens. So I'll be going over the methods and infrastructure and design methods of these electric roads. So the first method is by applying everyday technology into these roads. So on the right, or on the left-hand side, you can see this is a trolley bus in San Francisco. This trolley bus is using electricity from these cables into the bus so that it can transport and emit not as much carbon into the atmosphere as regular buses would. With these buses, they're strictly in San Francisco. They have to follow the path of the cables. And on the right-hand side, we see a cable cart. And this cable cart is getting electricity from the cables from the ground. This is another example of everyday modern technology with electricity. Again, these trolleys are restricted to their transportation and means to go. This is also in San Francisco. And so moving on with the first method, would be using power conductors. So with these power conductors, they would be placed inside grooves in the middle of the road, similar to a slot car, and it would power the car and the vehicle as they're transporting. So with electric vehicles, their lifespan for batteries lasts about 3 hours. So the problem is the stationary charging, it takes long. So with these rails, the stationary charging wouldn't be involved as much anymore. These batteries would be charged along the way as driving. So with the semi-trucks transporting, semi-trucks can't strictly solely depend on batteries alone. The batteries have to constantly be charged because these trucks to go from SoCal to NorCal won't last as long unless there are rails or electric road helping the battery recharge the truck along the way. A second method is used by Simon's Engineering. They use pantographs, as you can see in the next slide. Oh, so this is an example before we go into the pantographs of the rails that are used. So you can see these are how they would be manufactured into the roads. They're kind of blended into the road, as you can see. So the pantographs. So the pantographs, how they work is when a vehicle, specifically how Simon's designed it to be is the semi-trucks. This vehicle would drive underneath the cables and an arm would reach out. And as the car is driving, the battery for the vehicle would be charging. And if there is traffic, for example, in the way, the vehicle will be able to release the arm as it's doing the turn signal to go into a next lane. It would be independent for a little bit and can go back into its lane to charge again. As you can see in the top right, that is the arm extending down. So the infrastructure of these roads. So with the cost and funding, it all depends on the design and methods of these roads. To go about the rails, for example, those would take a lot longer. So as mentioned before with the schedule, that schedule was based on the pantographs. So with the pantographs, the roads would be manufactured for about, like for a road, it would be about 3 years. Whereas with the rails, it would take about 10 years to do a single road. So you get your pros and cons with these roads. You can have the pantographs that can contribute to the trucks, and also with the rails can contribute to both trucks and cars and can contribute to being an 80% efficiency rate for both vehicles in transportation.
So moving on, I decided to look at the maintenance and security of electric roads. So like any other technology, cars driving over it will cause it to degrade over time. And also the fact that this is a dynamic form of charging, you have to take into consideration risks on the driver's behalf, but also possibly pedestrians that might come in contact with the cars after. So the first thing that I decided to look at are long-term mechanical characteristics. So researchers at the Polytechnic University of Italy in Torino, specifically at the Department of Structural Engineering, had looked at a specific style of charging called inductive charging. And this diagram basically shows you a picture of how the electric road would be laid out. So as you can see, here are the copper coils that are beneath the surface of the road. It's about 60 to 70 centimeters below the top of the road. And on top of it, encasing it, is a layer of either a cement asphalt mixture or traditional asphalt, which is what regular roads are made out of typically. So with their research, they wanted to figure out which material would be best suited for electric roads for a long period of time. And they found that given their simulations running both lightweight vehicles, about 2,000 pounds, to heavyweight vehicles like semi-trucks of about 99,000 pounds, they found that CAM and asphalt had performed differently. So in terms of CAM, which stands for the cement asphalt mixture, it actually fared less well than traditional asphalt roads in terms of how long it would last. Because of the way heavy vehicles drive over it, the CAM doesn't have as much compressive strength and deteriorates faster over time than traditional asphalt. Now, that being said, CAM is significantly cheaper than asphalt, and asphalt actually fared worse over time when taking into consideration only lighter vehicles. So key takeaways from this study is that both types of road material had exhibited a 20-year lifespan, with the caveat that the CAM was more suited for roads where lighter vehicles would be traveling over them as opposed to heavier vehicles. So if there was a road in which you'd expect more heavyweight vehicles like semi-trucks to be driving over, then you'd have asphalt as the main component for the road. For the next long-term characteristic, we decided to look at the voltage stability. And this basically has to do with electric roads deriving their power from generators or solar or the power grid. And the way it works is that cars traveling on the electric road create a voltage potential. And with that potential, they're able to create charge and basically transfer power from the road to themselves. But this creates an effect where it causes voltage spikes back to the grid, and those spikes are actually undesirable and they could lead to damaged components. So in the research that was conducted at Cornell and Nanyang University of Singapore, the researchers had found that there was a max road length of about 4 kilometers that could be used for a typical electric style road, with slight improvements that could be made via the use of solar panels charging the roads. You have to take into consideration though that with using renewable energy from solar panels, this could create concerns with the duck curve and using renewable energy during parts of the day where energy isn't necessarily needed as much. And also in their research, they had found that maximum number of vehicles per 4 kilometer stretch was only about 4 cars per lane. And that basically leads to the key takeaways of, given the current technology, you could only have about 4 kilometers of road and also 4 cars per lane to prevent long-term damage to either the cars or the grid. Moving on to the safety of the drivers, researchers at Southeast University at the School of Transportation had decided to look into partial wireless charging lanes versus fully wireless charging lanes. So the reason being is because partial wireless charging lanes are cheaper to implement because, as you'd expect, it's only part of the road that has the charging capabilities as opposed to the whole road. Now this presents several issues in that cars wanting to take advantage of the charging would have to slow down and spend more time in the wireless charging lane to basically reap the benefits. And because of that, if you look at this picture right here, there is a time in which the car is slowing down that they are basically prone to having either a front or rear end collision with the car ahead of them or behind them. So in their study, they basically quantified the amount of risk that a driver would have driving on these PWCL lanes and turned them into these figures called time expected time to collision and time integrated time to collision, otherwise known as TET and TIT. And they use that in combination with what's called an intelligent driver model to basically simulate how a real person would react to the cars in front of them slowing down or speeding up. And it's interesting to note that this model, although it's a simulation, it's actually pretty accurate because of the data that's being fed into it. So the data data was taken from a study in Hollywood where they were taking into account driver reaction times and behaviors. So that basically helps make sure that the researcher's study is fairly accurate. Now, looking at some of their data, here you can see that there is the most amount of risk in cars that exhibit the lowest amount of charge. Now, this stands to reason because cars with lower amounts of charge would like to spend the most time in these PWCL lanes. Therefore, they would slow down the most and cause the most risk for crashing into each other. Now, going into the second and third scenarios where cars have increasing amounts of charge, it becomes apparent that there is less risk of crashing. And in the third scenario, where most cars are fully charged, there is practically no risk for collision at all because cars wouldn't be inclined to stop as much. Now, finally, we looked at the pedestrian safety. Now, this is really only an issue in which charging styles such as conductive is used. You could refer to the style of charging called pantographs, where the car is actually connected physically to a wire. And in some cases, that connection causes there to be a potential to be built up on the body of the car, which could theoretically transmit current into a person and shock them. So in this study from Lund University in Sweden, researchers had created their own charging system and electric car model, and also a simulated model, and basically researched whether or not a person touching the car right after it finishes charging would cause a shock to them. And in using 3 test cases, so normal operating conditions, so let's say the car is driving through and there's no problems with the ERS or everything is working as expected, at most the person would experience about 2.25 milliamps of current, which is considered to be under the safe limit. So at most the person would receive a tiny bit of shock, if any at all. And then for the next scenario, they tested if there was a loss of connection to the ERS, which is basically this rail right here. And if there was a loss of connection to the ERS, that would basically mean that the circuit inside of this car would cause more current to flow through the person touching it. In that case, the person would experience about 10 milliamps of current flowing through their body, which would result in like a severe shock. And then finally, worst case scenario was tested in that there is an insulation fault, basically meaning that all of the charge that's built up into this car would have no place to go besides ground, and it would go into the person, and that would lead to a fatal amount of current going through them. So a key takeaway from this study is that you need to have technology put in place to make at the vehicle level to make sure that any sort of problems that might occur when using conductive style charging would make sure that the body of the car isn't prone to shocking anybody that may or may not come in contact with the vehicle.
Now, in order to implement these designs and ideas, one of the main problems, of course, is costs and funding. Taking into account everything that we need, such as the process of design, labor, manufacturing, and implementation, requires a large sum of money. Specifically, we need money for personnel, materials, and construction. We have calculated a rough estimate of required funding through our gathered research and will be elaborated upon later. Although there are many different variables that go into careful consideration of this project, we will go over the general standards of the required budget. So first off, we have installation costs. Since the idea of eRoads and dynamic charging is essentially private and unknown to the public, it is not yet widely commercialized. Therefore, we can only talk about rough estimates of our budget. According to Chowdhury, currently the price of installation per kilometer ranges between $250,000 to several $1,000,000. In his team's research, they found a general equation to use for installation costs. As you can see the equation. Basically what this shows is that the cost of installation at road segments is assumed to be proportional to the length of the road segment. With this, if it were to be implemented across the country today, it could equate to millions and even billions of dollars for just installation. It is important to be efficient and cost-effective with our budget and optimize our design and plans in order to fit the given budget. It is also important to note that we are using dynamic charging instead of stationary charging. This is important because the total cost of one stationary charge system is close to $12 million, while dynamic charging units are closer to 9.5. As you can see in the graph, that dynamic charging costs significantly less than stationary charging. So moving towards a dynamic charging system would save us a lot more money. And now we move on to labor costs. Although design, installation costs, and budget are essential to the operation, labor is also a very important aspect of cost. The infrastructure for wireless charging requires cost for construction, which is variable depending on the geographical region. So what this means is that the cost of labor is largely dependent on regional fees. It's not a fixed ratio or amount. And so in our research, we assume that workers are working at least a minimum wage, and taking this into account, the cost of labor will amount to over 100 millions of dollars. We must keep this in mind as it will affect the construction and success of our project and our budget. And lastly, we have materials. Another aspect of the budget we have to consider are the components and the materials. If the parts are mass produced, a significant change in cost is expected. As a result, due to the anticipated cost fluctuations and variations, it is reasonable to perform various cost scenarios. Mass production of the components will generally lower the cost overall in comparison to custom-made production. There are several parameters that we have to account for, such as battery, power transmitters, and inverters. As you can see in the diagram, we have average battery costs for electric vehicles. From this information, you can see that the most expensive battery is close to $1,000 and the lowest is $220. In order to optimize our budget and allow for any increase in cost, you can assume that we will use the higher price to determine our cost. In addition, the power transmitter has come out to cost between $400 and $600 per meter, while the inverter cost is between $50,000 and $60,000 per unit. Again, taking into account how much distance we have to cover with our project, adding up these costs could easily enter the 100 million to $1 billion range. Kind of the last thing I want to talk about before we get to the end is our funding. So again, these costs, we will require money. So what we ask is funding for our project. So just to fit our budget, which is our $2.2 billion, and any government assistance and approval we can get. Also any money that we can get from Caltrans, as long as we get funding to meet our projected budget, we are flexible with our options. And now to conclude, with the increased use of electric vehicles and continued deterioration of the environment due to the greenhouse gas emissions, it has become apparent that greener transportation is a step we should take. The increased need for electric vehicles has prompted us to believe that eRoads are the way to go. By making eRoads standard to society, we can help eliminate the need for traditional gas-powered vehicles and make EVs the new norm. With this said, we can limit the amount of greenhouse gas emissions and create a brighter and greener future. It may be a large risk to take, but worth it once we put it in motion. Sustainability has never been more important, and we can take the first step together through eRoads.
Thank you so much. And that was our presentation. Here are some of our
Thank you.
references.
Thank you so much.
Thank you.